In this video, we're going to derive and find the expression for electron concentration in conduction band. I'm taking an energy band diagram where this is conduction band and this is valence band, where the bottom edge of conduction band is called EC and top edge of valence band is called EV, and the difference between these two is the forbidden energy gap EG. And we're going to call this as EC top, the top edge of conduction band, and EV bottom, the bottom edge of the valence band. In order to find the electron concentration in the conduction band, because that's the concentration which will contribute to the conduction of electric current. So that's why that concentration is important for us. So now to find the electron concentration in the conduction band, basically at each energy level, let me take this is energy level E. So at this energy level, if you know the number of states and if you know the probability of that state being filled by electrons, let's say that is the probability of being filled by electrons, then we can say the total number of electrons at this energy level E is given by the product of this, the number of states present and the probability of these states being filled by electrons. To find the total electron concentration in conduction band, we need to basically add at each and every energy level. Even though in reality the energy levels are discrete, but we have assumed that the energy levels are concentrated in a small range, so we're going to call this a band of energy levels. That's why we called it a conduction band, which means we assumed that these energy levels are basically continuous. So in that case, we cannot directly take this approach. Instead of adding, we should be integrating in order to find the total concentration. Now, similar to this analysis we did, we need to first find the number of states per unit volume at each and every energy level and find the probability of those energy levels being filled by electrons and multiply those two and integrate it over this range from EC to EC top so that we would get the total electron concentration. Now, in order to do that, we need two functions. One is how are these energy states distributed in this conduction band. So that is given by a function GC of E, which is called the density of states in conduction band, which is given by square root 2 over pi square times effective mass of electron mn star over h cut square whole power 3 by 2 times square root of E minus EC. This function is valid for E greater than EC. Now let us see how this function basically looks like. I'm taking energy level on y-axis and GC of E on x-axis, where this point is EC. And if you look at this function at E is equal to EC, and this function is valid for equal to EC as well. At equal to EC, this function value is 0. So basically we start with 0 and it increases like this. So which means as we are going above the EC level, the number of states present are increasing. Now we know how the energy states are distributed in the conduction band. Now we need to find what is the probability at each and every energy level that these energy levels are filled by electrons. So that is given by Fermi-Dirac distribution function, which we have already seen in previous videos, where f of E is given by 1 over 1 plus e power E minus EF over kT, where EF is the Fermi energy level. And this function basically tells us at a given energy level, what is the probability that electrons will fill that energy level. So let us plot how this function looks. I'm taking energy level on y-axis and the function Fermi-Dirac function f of E on x-axis. And we know that f of E can take values between 0 and 1. And of course, to plot this function, we need to assume some temperature and assume some EF. So I'm taking some temperature at which the function would look like this, let's say, where the probability is 0.5. I'm assuming the Fermi energy level is somewhere here. And EC we have seen is here. Because in our analysis, E is a continuous variable, so we cannot talk about the number of electrons at a given energy level. Instead, within a given range, we can talk about electron concentration. So that's why I'm taking an incremental distance where this value is dE, over which I'm trying to find what is the electron concentration. So this would be the range, and similarly if we find out here, So in this range, the probability of these energy levels being filled by electrons is given by this function f of e. Now in order to find the differential electron concentration, which I can say is dn, can be given by gc of e, the density function, times the probability distribution function Fermi-Dirac's, which is f of e, times the differential energy level. This will be the electron concentration in that energy range. Now in order to find the total electron concentration in the conduction band, we should be taking integration on both sides, so that we would get n is equal to integration of this function from EC to EC top, which means we are covering the entire conduction band, where we have gc of e times f of e times dE. Now in order to see what this function basically looks like, the gc of e times f of e, because we are trying to find the area under this product function. So let us see what this function looks like. Product of these two functions is resultant will be plotted in this graph, where I'm taking the y-axis to be the energy level and the x-axis to be the product of these functions, gc of e times the Fermi-Dirac distribution function f of e. So if you take the product, below EC, the function value of gc of e is 0. So whatever is the value of f of e, it doesn't matter, it will be 0. And now at e equal to EC, the value of gc of e is 0, times f of e would be 0. So taking EC, here the product would be 0. So we're starting with 0. And as EC is increasing, basically the f of e is decreasing. So initially it would increase, and later the dominance of Fermi-Dirac distribution function would come into picture, where it steeply drops towards 0. Now we are basically finding the area under this curve, which would give us the electron concentration in conduction band, which is n. And we can observe from this plot that the function is approaching 0 even before it reaches the EC top. So we can say, instead of taking EC top as the upper limit, we can take infinity as well, so that it doesn't change the result. So I'm going to rewrite this expression, given the integration is from EC to infinity, and we have this function gc of e times f of e dE. For simplicity, let me take these constants to be a value c, and I'm going to write this expression by substituting the function gc of e and f of e, so that this integral would become. Now this function cannot be directly solved because we have a function here, the Fermi-Dirac distribution function, unless we make some assumptions. Now frankly, when we actually took f of e, we just assumed ef to be somewhere. But in fact, we don't know where ef is precisely. So I'm going to do an assumption saying that what if e minus ef is greater than or equal to 3 kt? In that case, this exponential would be far greater value compared to this one, which means I can rewrite this expression as, so the lowest value of e minus ef will be ec minus ef. If this itself is, let's say, greater than 3 kt, then we can say that this assumption is valid. So this is a very important assumption that we are making, where ec minus ef is greater than or equal to 3 kt. And this assumption is called Boltzmann approximation. By doing this approximation, we are getting a function like this, which is e power minus of something, which is very similar to Boltzmann distribution function. Now solving this is purely mathematical. To solve this integration, let me assume that e minus ec over kt is equal to some variable x. And we can also say that e is actually changing from ec to infinity, and similarly we can say x would be changing from, when you substitute ec in this, we would get x to be 0, and when you substitute e to be infinity in this expression, we would get it to be changing to infinity. Now the relationship between e and x is, so wherever we have dE, we can substitute this with kt times dx. We can write e minus ef over kt as, and this can be further written as e minus ec over kt plus ec minus ef over kt. So this equation, e minus ec over kt, we defined it to be a value x. So now taking all this, let me rewrite this particular expression here in terms of x. Now we can write this as c times kt over 3 by 2 e power minus of ec minus ef over kt, where ec and ef are constants. That's why we have taken this whole term outside, times integration 0 to infinity x power half times e power minus x times dx. Now this particular integral is a very standard integral in mathematics, which is actually called a gamma function. This can be written as just this integral 0 to infinity x power 3 by 2 minus 1 times e power minus x times dx, where this is given by gamma function of 3 by 2. And its value is given by square root of pi over 2. Which means now we can rewrite this n, the electron concentration in conduction band, by substituting the value of c that we have seen here and the integral value, which is square root of pi by 2. Then we can write n is equal to c is square root 2 by pi square times m n star effective mass of electron over h cut square whole power 3 by 2 times we have kt power 3 by 2 times square root of pi over 2 times e power minus of ec minus ef over kt. Now we can simplify this to be n is equal to 2 times 2 pi kt times mn star divided by h square whole power 3 by 2 times this exponential, which is e power minus of ec minus ef over kt. And now we can write this expression n is equal to this whole constant to be n suffix c times e power minus of ec minus ef over kt. So this is our final expression for the electron concentration in conduction band, where Nc is given by this constant. We got the final expression, which is equal to this, which is given by n is equal to Nc times e power minus of Ec minus Ef over Kt. And we can use this formula only when Ec minus Ef is at least greater than or equal to 3 Kt. And this is the assumption we did while going through the derivation. And this assumption is called Boltzmann approximation. Let us look at this n and try to understand what these two terms mean. So we have Nc one term and another exponential term. We know the units of n, the electron concentration in conduction band, which is number of electrons in conduction band per centimeter cube, or say per unit volume, which means the right side units also should be same. But if you see the exponential, it basically doesn't have units, which means it's going to give some fraction or some number. And we have assumed already that Ec minus Ef should be greater than or equal to 3 Kt, which means this exponential value would be a very far less value compared to 1. So this, we can say this is basically telling us the probability of filling these available states. So Nc basically means the effective density of states. Now what it means is n tells the number of electrons per centimeter cube, which is given by the effective density of states, which is number of states per centimeter cube, times the probability of all the states being filled by electrons. This is a very important expression. We will be revisiting or using this expression again and again in this course. And every time, remember when you're using this formula that this condition should be satisfied. Only then this formula can be used.